Morning, everyone. So today we're going to be finishing up with our Chem 11 review. We're going to start off with a quick practice of eliminating excess. Basically, we looked at stoichiometry in yesterday's lesson. After we do that, we're going to do a quick twist over into a titration. We're going to see titrations come back in our Chem 12 course 2 or 3 times. Although the setup might be a little bit different from unit to unit, overall the calculations end up being the same. So if you're comfortable with what a titration involves and the calculations, it'll help you out in the long run. We'll also finish off with a little bit of a mixing question, which will also show up in chapter 3. So let's just practice through a quick limiting excess question here, just for a warm-up. I'm going to give you this reaction. When 14 grams of aluminum, sometimes they like saying aluminium. Aluminium is still the same element, aluminum here. When 14 grams of aluminum react with 34 liters of oxygen gas. I'll give you the expression for you here. We have aluminum and we have oxygen. Right. We can predict, this is a synthesis reaction, so they basically smush together. It's going to be a compound that has Al and O inside, but do still double check that you've written the formula correctly. So in this case here, aluminum is a +3 charge, oxygen is a -2. The compound needs to be Al2O3. The other thing to check here is this is a Skeleto equation, so this one here is unbalanced. What's the lowest common numbers I would need to actually balance this one here? I would need, so double the odd number here. This would triple that. 2 times 2 ends up making 4, so there we go. So that's the lowest whole number ratios. How do I know this is a limiting excess question even before I write the ABCs? Because they actually tell me, by the way, you have 14 grams of aluminum and you have 34 liters of oxygen. Anytime you have information for more than one chemical, there's a good chance that one of these numbers might run out first. So, case in point here, they're going to ask you which is limiting, which ingredient ran out first. B, I want you to find for me how many Al2O3 molecules form, how many are produced, and then C, calculate the excess left over. And remember, excess is quoted in the units that we have it. So if aluminum turns out to be excess, give me the grams, it's extra. If oxygen is extra, tell me the volume that's extra there. Again, I encourage you just to pause the video, try it out for yourself, and then when you come back, just check your work. Again, our strategy from yesterday was, I don't know which one runs out first. I just totally made up these numbers. So let's do our strategy. Let's go to a product. In this case here, it's nice because I only have one product. And in this case, because part B actually asks you for molecules of this product here, if I'm trying to do part A and B together, what I can do is I can individually take turns. If 14 grams of aluminum get reacted, if all of it's gone, how many molecules of Al2O3 would I get? And in a similar fashion, I'm going to say, well, what if the other ingredient ran out first, just 34 liters, how many molecules can it make? Whichever makes the smaller number is the one that's limiting. So let's just try it out here. We're interested in finding here how many molecules. If you're going to shorthand the word molecule, don't make it any shorter than MOLEC, because if you shorthand that, it looks like mole, that looks like mole here. So molecules of aluminum oxide, and all we're going to do is we're going to change our starting condition. Our starting condition at first is going to be, what if the aluminum ran out? As a second calculation, we're going to figure out how many molecules of Al2O3, what if 34 liters of oxygen runs out? Both of these are going to take 3-step conversions because our only connection between one chemical and the other side here is going from moles over to moles. So I don't quite have moles yet, so let's go grams to moles first. Then I'm ready to use mole ratio. For every moles of aluminum, how many moles of aluminum oxide, and then I could have stopped at aluminum oxide there, but since they want to get to molecules, I may as well multiply Avogadro's number in. In a similar fashion on the other side here, it's going to be, well, liters to moles, and then for moles of oxygen, over again to moles of aluminum oxide, we're going to find that this last Avogadro's number formula, it's exactly the same. That's why I said you could have actually stopped it here and then just multiply Avogadro all at once. But since I want to do A and B all together, you may as well just go straight through. So aluminum has a molar mass 27, so that's 6 with the G for 1 mole. The mole ratio says for every 4 in front of aluminum, there should be a 2 in front of Al2O3. And then 1 mole is always an Avogadro number, 6.02 E23. Crunch those through. 34 liters of oxygen as a gas STP, 22.7 liters as a mole for a gas. We have for every 3 in front of oxygen, there should be a 2 in front of Al2O3, and then you multiply that same Avogadro's number. Essentially, we're testing them independently and saying, based on the amount of each ingredient, how many molecules should I get? In the first one, I should get 1.56 times 10 to the 23 molecules of product. On the other side, 34 divide 22.7 times 2 over 3 times Avogadro's number. In a similar fashion here, 6.01 times 10 to the 23. Again, there's nothing that says these numbers here have to be close, because remember, these numbers are just based on how much I actually bought. If I bought a ton more of oxygen, this number here would be way bigger. We look for the smaller number, don't just leave it like that. The smaller number in this case here is the 1.56, so that means I didn't quite have enough aluminum. The aluminum ran out first, so give me some summary statement here. Therefore, based on my problem, I know aluminum is limiting. Sometimes they use the word reagent. Reagent just means reactant. Just want to introduce that to you. So aluminum is the one that ran out. And by the time it ran out, part B, 1.56 times 10 to the 23 molecules of your product, Al2O3, formed. Also in the theoretical world, also just by calculation, if everything goes according to plan, I get 1.56. I never get up to 6.01 times 10 to the 23. Right? I'm going to show you those 2 ways of calculating the excess again. Now I found out aluminum was limiting. Aluminum was expressed in grams. I want to know how much of this grams is actually left over. So just based on what we did from yesterday, method number 1 was, let's start off with the aluminum. Let's figure out how many liters of oxygen are actually consumed by the time the 14 grams of aluminum get used up. The nice thing here is we can actually start with the limiting, because I guarantee this whole 14 gets used up. I already have a lot of the numbers, so molar mass was 27 grams per mole. But this time for your molar mass, for every 4 moles of aluminum, I'm just going to jump over to oxygen. So the nice thing about the mole ratio is it doesn't just give me a link between reactants and products, it gives me a link between reactants and reactants as well. So 4 and 3 there. Because oxygen is a gas at STP, 1 mole is going to be 22.7 liters. Crunch your way through. 14 divide 27 times 3 over 4 times 22.7 gives me here, you actually use up 8.8. 368, so 8.83 liters get used up. So actually not a lot. I actually had some 34 liters. Chemists do this all the time. Let's say aluminum was a much more expensive equipment. You definitely want to make sure all the chemical completely gets used up. You might purposely toss in an excess, purposely pump in so much oxygen, so plentiful anyways, and basically it's guaranteed to consume up all the aluminum that you have. So we do a subtraction here. Out of the 34 liters that I initially purchased, I minus off our 8.83. So 34 minus off this answer gives me here 25.2 liters. Right? So lots of extra remains. That's one way of doing it. Again, you just need to do one or this other method here. The other method, based on the way I solved it here, is we're going to do the subtraction. Well, I see that the oxygen could have made a lot more. So let's go with this 6.01 number, coincidentally really close to Avogadro's number. If I take this number, I minus off that 1.56 times 10 to the 23. How much could have formed? 6.01 E23 minus 1.56 E23. I could have made an extra 4.45 times 10 to the 23. I'm going to emphasize here, this is how much could have formed. And also I want to emphasize here, this is still Al2O3. This is not your answer because this is your product. This is how much cake you could make. Now, how much of the oxygen ingredient is sitting around just waiting? If you just bought more aluminum and you just kept producing more, I can make an extra 4.45. So we still need to do a calculation. How many liters of oxygen are just waiting, just sitting around extra to make this new amount? 4.45 times 10 to the 23. This one here, it's helpful if you just write all the units so you know where we're converting. We're going to use Avogadro's number once more just to get back to moles. Then we can use our mole ratio for every 2 parts aluminum oxide. There is 3 parts of oxygen. And because an oxygen is a gas at STP, 1 mole is 22.7 liters. This one gives me here 4.45 E23 divided by 6.02 E23 times 3 over 2 times 22.7. This one gives me, in a similar fashion, 25.2 liters extra. So it's the ingredient that's extra. It's the oxygen that's sitting around. I had so much of it lying around. That's how much remains. Your stoichiometry problems will not always be limiting excess, but if you're okay with limiting excess, you're more than comfortable doing these 2-step, 3-step sort of conversions. Right? Again, in today's lesson, I want to recap with you two big techniques that have come back in Chem 12. First technique I want to recap with you here is a titration. A titration is a chemical technique. The whole point of a titration is to find some unknown concentration. So let's imagine I start off with a bottle, and this bottle here is labeled (molar HCl). Right? So it's known that it is hydrochloric acid, but what's unknown is the molarity. I don't know if this is the really strong, the stock container would be something like 12 molar, really, really dangerous, or maybe I diluted it with a bunch of water. Maybe it's only 0.1 molar, something like that. The goal of doing a titration is to find this unknown concentration. How we're going to do this, in this case here, it's actually an acid-base titration. We're going to run a reaction. We're going to react this HCl purposely with a base. I'm going to use NaOH. This one here is an acid-base neutralization. We expect it to produce a salt and water. This one ends up actually producing table salt and water. Fine, no problem. And what we're going to do is we're going to do this so precisely that I'm actually going to use the NaOH. Effectively, I want to count how many HCl that it reacts with. I want to stop before there's any excess, and then I can do stoichiometry to figure out, based on how much base I dropped in, how much concentration the acid is going to be. So here's how this is going to work here. For a typical titration setup, we set up a long glass tube here called a burette. The burette here, our burette here is a 50 ml burette. For some reason, the 0 mark is on top and the 50 ml mark is on the bottom. What I tell people is just fill it something more than half. And this time I'm going to fill it, so let's fill it, let's say right now the marking, maybe I'm at the 10.00 marking. That doesn't mean there's actually 10 inside this burette here, because the 50 is down there. That means there's some 40 in here. But what I'm going to do is I'm going to take an initial volume reading. So that's the volume initial. And for this setup, although you could have put the acid or the base inside here, because my unknown is the acid, I'm going to put the base. The base, I'm going to give you the concentration. Let's say it's 0.2500 molar NaOH. The thing is, for a titration here, although we are interested in finding the unknown concentration of acid in this example, the other chemical, I have to know the concentration. I can't react one thing unknown with another thing unknown. There's too many variables there. All right? So there we go. I know the concentration of the base, 0.250. I actually know it to a lot of precision. And what I'm going to do here is I'm going to slowly drop in this base here. For my acid, I'm not going to use up my entire stock bottle. All I'm going to do is I'm going to take a small fraction of it. That fraction is usually called an aliquot. And usually for the aliquot, what we do is we use a pipette. I'm going to pull out, let's say, 10 milliliters of my unknown acid. So this is from my pipette, and this is a molar HCl. Right? So at this point here, I still have no clue how concentrated this acid is. This one here could have a lot of H pluses around. It could only have very few H pluses around. I don't know. And how I'm going to test it is I'm going to test it against how much base do I slowly drop in. There's a little stopcock valve on the burette here. You can steadily open and close it. And basically, how much can I drop in to kill off the H plus? If this thing here is not very concentrated, you don't need to drop in a lot. Very small amount of titrant, very small volume would already hit the equivalence point. If this is really concentrated, you're going to run through a lot of your burette. And the hope is we're going to have enough in the burette for one trial here so that you don't have to reload in between. Every time you reload, it's actually going to introduce some error. So effectively, this is what's going to happen. You're going to have your NaOH, I know the concentration. You're going to slowly open and close the burette valve here. As you start dropping in the hydroxide, right, NaOH here just provides for you the hydroxide. The Na is just a spectator, it just sits around. As long as the hydroxide finds an H+, it gets neutralized. It's not going to be overly basic. And what we're going to do is we're going to look for the point. I'm going to drop the hydroxide slow enough that the hydroxide slowly kills off the H+. Oh yeah, that hydroxide found the H+ here. I'm going to look for this point where I've just perfectly added in just the right amount of base to just the right amount of acid. Remember, I have no clue how much acid there is. The difference is going to be how much volume before this happens. We're going to add the base until we hit something called the equivalence point. Just going to introduce that name to you here. We're going to run our titration until the equivalence point. The equivalence point is when the moles of H plus actually equal the moles of base. And again, using this analogy here, effectively I'm figuring out how much base that I need to drop in until I can count how much H plus there is. If it's really concentrated, lots of volume before it happens. If it's not very concentrated, not a lot of volume. Once you hit this equivalence point here, you're going to drop in the hydroxide. It's no longer going to be able to neutralize any acid. That's the point I want to stop. It's totally possible that you can actually overload it. You can actually, whoops, I slipped my hand, and basically the base is dropped in there. This now becomes overly pink here. Then you need to reset. I don't want to actually have any excess because I want to make sure the amount of base I've dropped is a really good count of how much H plus there is. At that point, when that happens, we would then take another volume reading, wherever it is. I'll show you this to you in a second here, and this is going to be called the final volume. Again, whatever number that is, that's not actually the number that's in the burette, because what we're going to do is we're going to take a difference. The difference between my starting reading and my ending reading, that's actually how much volume I dispense, and then eventually it boils down to a stoichiometry problem. One other detail before we practice that stoichiometry here. The other detail, unfortunately, HCl and NaOH, both of them are soluble. Both of them dissolve fully. It's not like any of them powder out. And also both of them are colorless. So even though I'm interested in this point where I've just put in enough base to kill off the acid, I need something to indicate in the solution when the reaction is done. What we're going to do is we're going to, actually in chapter 4, when we do our acid bases, we're going to learn many different indicators. The indicator that we did in our lab is we use the indicator here, phenolphthalein. This in some sense here is a totally irrelevant chemical, but basically for phenolphthalein, there's a special pH where this phenolphthalein actually changes color. Just for simplicity for the time being here, in acid, it actually stays colorless, whereas in base, when I alluded to it turning pink, it's actually the phenolphthalein that actually turns pink. So before you actually do the titration, you take your starting reading. Before you actually add in any base, make sure you drop in a couple of drops of phenolphthalein. It just needs to be present. It doesn't need to be in high quantities. And basically, it's there to detect whether it's overall acid or overall base. So at first, when there was a lot of H+, you drop in a little bit of hydroxide. Because the hydroxide gets killed off and there's a lot of H+, the phenolphthalein stays colorless. As you steadily get closer and closer to the equivalence point, basically you slowly kill off the H+, there's going to be more base every time you drop in the NaOH. It's going to stay pink for a while. You swirl around. As long as it can find H+, there's still a net excess of acid, so it's going to stay colorless. As the pink color stays longer and longer, we look for this equivalence point when I actually have just one hydroxide, and now it can't find any H+ left over. Because it can't find any H+, now it is basic. Now the phenolphthalein suddenly says, oh, it's basic. I'm going to turn to a pink color. So basically, when the color change actually switches, I know to stop. If I accidentally load too much NaOH, it becomes overly pink. I need to reset it up again. For an indicator here, the special point where it changes color is actually given a new name. That special name is called an endpoint or transition point. We're going to get all into this in our course. Endpoint or transition point is when the color change occurs. So just introducing to you, it's totally possible that the color change occurs at a wrong pH. That would be a silly indicator to put in. You want to use an indicator that roughly changes color where you expect the equivalence point to be. Again, more on that later on in the course. So that's the typical setup here as well. Because this is a lab, you typically want to do this a couple times just to make sure it's not by fluke that you ended up getting certain numbers. This is how the data is usually recorded. We had 10 milliliters of unknown acid. Although I didn't know the concentration, I decided to test 10 milliliters worth of this unknown. If I had pipetted 25 mils, I could do 25 mils. It's a known volume of an unknown concentration. What I'm going to tabulate for you here is we're going to do this a couple different tries. Let's say try 1, try 2, try 3. Trials are basically repeats of the experiment here. I'm going to note down for you what's the starting reading of the burette. So let's call that VI. Remember, that's not how much base is actually in there. Let's say my VI started off with 10 milliliters. It actually is some 40 inside, but I don't really care about that number. What I'm going to do is I'm going to read the VF. After this one here is turned pink, after I've stopped, I just take another reading of the burette. This number will be something larger than 10. So let's say 29.25. Right. Both of these volumes here are not how much liquid is in the burette, but knowing both of these volumes here actually helps me find a difference in volume. And basically by subtracting the two, I can go 29.25 minus 10. This one gives you 19.25 milliliters is how much you actually added. So let me just note down again. This is the initial burette reading. This does not mean you've loaded up with 10. This is the final reading, and in this case here, I have this is my NaOH solution where I know the concentration is the 0.250 I gave you from earlier. So I noticed that from the first trial, the first trial took about 19. I want to do my second trial. I need to have a fresh aliquot, so wash out the Erlenmeyer, take out another 10 milliliter aliquot, fresh H+, and be ready to drop in more acid. Because the first trial took about 19, I know I have between 29 and 50. I still have a good, let's say 20 or so in there. If you want to be a risk taker, you could totally, okay, yeah, let's have the burette. Now my starting reading is 9.25. I should have, give or take, about 20 in there still left over. So let's do that. So you do your trial here, and lo and behold here, 29.25. It ends up, after your reading here, it ends up going 48.35. Okay, just totally making up some numbers. Oh, that's when it turned pink. That's when I stopped. 48, you're going to actually realize is actually cutting it really close to the burette end. Basically, 50 is the last mark I can read. There is going to be some leftover volume that has dropped lower than the 50 mark, but because I don't have the markings there, I can no longer read the volume. I basically would need to start it over. So I really pushed it to 48.35 here. Let's try it out here. 48.35 minus 29.25. That one gives me here 19.10. Usually because the trial one is just totally a guess. Usually I wouldn't do the first one too exactly. I just sort of, let's dump in a couple. Oh, it turned pink. Let me know roughly what it is. And then what I would do on the second trial is I go, oh, I hit 19. Maybe I overshot that. Maybe it was a little bit too high. Let me add in, let's say, 15 very safely. And then let's slowly drop it in a little bit slower between 15 and 16. Oh, no, it didn't change yet. You keep going slower and slower. Hopefully, the next trials will be even more precise. Now, I definitely don't have enough solution, right? If I started my initial volume 48.35, I only have about 1 mil. That's not going to be enough for the new aliquot. So what I'm going to do is I'm going to refill. Refilling between trials is no problem because, remember, we're going to take a starting reading, we're going to take an ending reading. Let's say I then reload the burette, so top it up with the 0.25 molar solution, right? And let's say I top it up, and now it says 15.00, right? It doesn't really matter. Usually I just say more than half so that I don't have to reload during a titration. And as I do that there, when I do the last titration, basically I open and close the valve again, and you drop in the NaOH, and this last volume here says 34.12. Right? There's no guarantee that your next trials are better than the first trial, even though the first one is sort of an approximate. What you're going to do is, as an experimenter, you're just going to look at all three numbers that you get. So 34.12 minus off of 15, this one gives me here a 19.12. Right? So first thing, I have a little bit of confidence because all three volumes are very similar. This is a good thing. Right? The whole point of titration is to be really exact, though. I noticed that, wait, my trial 2 and trial 3 are a lot closer to each other than trial number 1. What you can do as an experimenter in this situation, you might call this one here an outlier. This is a point that lies outside of your data reading. This one here, perhaps we overshot the endpoint. Perhaps this one here became overly pink. I didn't stop it at the right stoichiometry and actually just averaged the two close trials. If I average those two, basically you add those two numbers up and divide by 2, if you need the math for that there. That gives you here 19.11 milliliters. So on average, even though I tested two different samples of acid, on average, it is 19.11. Even though it was a lot of work to actually get to this number, at the end of the day, it boils down to stoichiometry. So let's see what happens here. We're going to have HCl and NaOH. I needed a balanced equation, so good. That was actually balanced for us here. NaCl and water. So far, we had an unknown molarity of HCl. Our whole job was to find that concentration. The NaOH, like I told you, I actually know the concentration that was given. Actually given to a lot of precision as well, 0.2500 molar. The volume that we actually needed to add in on average was 19.11. We had only averaged the close trials. If all three were sort of wildly different from each other, average all three, right? I'm trying to get some in between. And the whole goal is for you to try to take the base information that I know and try to get your way over to find the acid. I want to remind you here for the acid, remember, even though it was unknown concentration, I had decided to test 10 milliliters because that's what my pipette delivered. So I have 10 milliliters. There's no guarantee that this volume has to be close to this volume, but because they're linked in the stoichiometry, I can just use my mole ratio to actually figure out what it is. And all titration problems, we'll see it as chloride titrations in chapter 3. We'll see acid-base titration. We'll even see redox titrations in chapter 5. All of them boil down to this. Take the chemical where you know concentration and volume. What you're going to do is you're going to try to find moles because we want to do stoichiometry. We're going to do our mole ratio. Sometimes it's 1 to 1, sometimes just based on the balance coefficients. We're going to go moles over to moles, and then we're going to take whatever missing information, and we're going to be able to find the unknown. So in this case here, because we guarantee that there's no excess here, I'm just going to show it to you as a just sort of all in one long row here. I'm going to start off with a chemical that I know more. I have both a volume and a concentration. Which one's easier to work with? Well, concentration molar is actually a conversion factor. That one there is actually moles per liter. So that one there is actually going to be a conversion for you. Let's not start off with that. Let's start off with the 19.11. Although because we need liters, I'm going to convert that to liters. 0.01911 liters. So this is talking about NaOH. You don't need to show me the divide by 1,000. We're going to use concentration for 0.2500 moles in every given liter. That was the concentration given to you. The mole ratio does turn out to be a 1-to-1 ratio. For every 1 mole of NaOH, it's 1 mole of HCl. If you look at the units canceling here, liter cancels liter, we've now taken the base particles that we have, and we've now counted how much unknown acid there was. Remember, that was the number I'm interested in to figure out the initial concentration. In some sense, when you've done this titration, I had 10 milliliters of acid before. I've just tossed in an extra 19 or so. This final volume here has actually gone way up. I've actually screwed up the sample here. This sample can no longer be used. But if you know the moles of H+, the moles of H+ were initially pulled only from a 10 milliliter volume. So what we're going to do is we're going to take, this is the moles of acid that we get, and all we do is we want to divide out the volume. Initially, this was all in 0.01000. This was all in 10 milliliters worth of solution. Now that just looks a little bit more confusing. So usually what I do here, instead of doing this all over 0.001, usually I just bring it up here and I just say, it's sort of like multiplying the reciprocal divided by 0.0100. So as dividing, I'm going to remind you here, this is the initial volume, right? All this acid used to just be in 10 milliliters. Sure, I needed to toss in an extra 19 or so just to count the acid, but eventually this acid is divided by 0.01. Now we are very used to going top unit cancels bottom unit, top unit cancels bottom unit. In this case here, I actually want to keep the mole unit because I need moles on top and I need to actually pick up a liter unit on the bottom. So therefore we're just multiplying by 1 over, no units, and therefore we have moles over liters. So let's go here, 0.01911 times 0.25 divided by 0.01. This one gives me the unknown concentration to a lot of precision, right? I have 4 sig phase going through, so this is going to be 0.4778 molar HCl. And we've done our job. Even though I had to do 3 trials, even though we had to use this indicator to tell me when to stop, I've actually figured out what's the concentration of my unknown solution as 0.4778. And now that this solution here is a known concentration, we can now refer to this as a standard solution, or it has been standardized because I now know the concentration. You can now use this number to find some other unknown concentration. So in a titration, our goal is to find a concentration. We needed to know the concentration of one of them to find the unknown. If I now know the HCl, I can use the HCl to standardize yet another solution. Then we sort of backtrack and we say, well, how did I get the very first solution then? If I always need to know one before I can find some unknown, how would I get the NaOH? Well, maybe I got the NaOH from titrating with another acid. Well, how would I know the unknown for that unknown acid? We sort of get into this sort of endless problem. The other way we can actually find a concentration really well is to just make a solution. So if I take a solid, this solid here has to be a very special solid. We have to call it a primary standard. We'll see this a little bit more in chapter 4. A primary standard is an object that's solid and it's super pure, okay? Also super inert, that if you leave it out exposed to the atmosphere, it really doesn't absorb water, it doesn't react with carbon dioxide, things in the air, so that if I weigh out a certain mass, let's say I weigh out 1 gram of this material, I'm really confident when I dissolve it and I make a solution of it, I know it's actually 1 gram of my chemical. A chemical that is not a primary standard, sodium hydroxide by itself is actually not a good primary standard. Sodium hydroxide actually also comes to us as little pellets. The problem is the sodium hydroxide, even if you leave it out for maybe 10 minutes or so, you're going to find that it's actually starting to absorb the moisture in the air. It's actually going to steadily pick up some impurities. So it's not a problem. You can still weigh out 1 gram of the sodium hydroxide. The problem is because sodium hydroxide is sort of absorb some extra mass due to the water. When you say 1 gram NaOH, when you intend to make a solution of it, I'm not sure that the entire 1 gram that I weigh is actually sodium hydroxide. So that's why there's only a handful of chemicals. Baking soda is actually a really good chemical because it stays really, really pure. We want to make a solution really accurately with a primary standard, and then I can standardize for whatever else. How did they know the concentration of NaOH so well? They probably standardized it with an acidic standard. Again, more on that in chapter 4. Also, I want you to just notice in this problem here, it sort of looks like a C1V1 C2V2. We'll see that calculation very shortly here. What I've ended up doing is sort of like a V1 and a C1. I ended up having to divide the V2 over and I get a C. It looks very similar to a dilution problem. The part that you're always going to miss is this mole ratio. So if your problem is a 1-to-1 ratio, sure, C1V1 C2V2 ends up working. The second that I end up switching it out for you, let's try it out as a problem here. Let's say I have H2SO4. That's reacted with LiOH. This one becomes Li2SO4 and water. The second that the mole ratio is actually a little bit different, you're always going to be missing this step here. You're always going to be off by a factor. So long story short is don't use C1V1 C2V2 unless it's a dilution mixing style question, as we do in the next problem. Just to practice a little bit of stoichiometry here, let's say I do this titration again. Let's say I've standardized for the H2SO4. The concentration is 0.3500 molar. I happen in my burette, I had dropped in acid this time. Let's say I dropped in the acid, it was 12.16 milliliters. The concentration of base that I reacted it against was 0.4600 molar. And my question is, what volume of base from the burette would I have actually needed to hit the equivalence point so that I've just added enough H plus to kill off the base? It just boils down to a stoichiometry problem again. Start off with a chemical where you know both concentration and volume, find moles. Then you mole ratio over, and then you use the leftover number to find the unknown. This time I'm interested in finding the liters of LiOH, the liters of base that I need to add. I'm going to start off with the 12.16 in liters, 0.01216 liters. This is H2SO4. I'm going to use my concentration, 0.3500 moles for a given liter. The mole ratio says for every 1 part H2SO4, again, this is the part that you'll always miss if you just accidentally do a C1V1 C2V2. It's actually a 1-to-2 ratio. My recipe says for every one of these particles, it kills off 2 LiOH, 2 moles of LiOH, and this time I can actually use the concentration. Now we've jumped over to LiOH. Use the concentration LiOH, 0.4600 moles for a given liter. And there we go. When I factor all that through, 0.01216 times 0.35, don't miss the mole ratio of times 2, divided by 0.46. This now tells me here I would need 0.01850 liters, or you can write that 18.50 milliliters. Right? So do not forget to do the mole ratio. That just comes straight from stoichiometry, even though it was a little bit more work to actually get to these numbers. Right? The one last thing I want to review with you in this lesson, and then I'll finish off our Chem 11 review, is when can we use the C1V1 C2V2 kind of setup. When we can use it here involves either a dilution problem, or we saw a mixing style problem. And mixing is basically just 2 dilutions in one. Right? So I'm just going to do this by way of example here. Let's start off. Let's imagine I have on the left side 10 milliliters of 2 molar zinc chloride solution. Right? So I'm going to pour that in. I'm going to mix it with another solution. I'm going to color code it, let's say blue. This one here has a different volume, 20 milliliters. And let's say this one concentration is 1.60 molar. And let's make this zinc sulfate. You could totally just pour one beaker into the other beaker. I just find for calculation's sake, it's a little bit easier. Let's imagine we have a third container just sitting here, and it's just a collecting vessel. It's going to collect, you pour in the green solution, and then you pour in the blue solution. It's just going to collect both solutions up. Let's start off with the easy question. What's the total volume going to be? Well, the total volume, because I mixed in 10 and 20, the total volume is now going to be 30. So basically all the swimmers, all the zinc chloride in here, all end up swimming in a bigger pool. All the swimmers on the other side, let's draw them as triangles here. All those triangles end up swimming around as well. For these dilution and mixing style problems, we're going to be under the impression, unlike a titration, unlike the H plus actually trying to react with a hydroxide, we're going to assume that there's actually no reaction, which is actually not too hard to do in this problem, because in this problem here, we have a zinc compound and another zinc compound. Even if they try to do a double replacement, zinc swaps out zinc, well, we still have a zinc compound. So we're going to assume there's no reaction. What we're going to do in this problem is we're going to always do a dilution part first. So the dilution is going to be, we started from 10 milliliters and we want to end up with 30 milliliters. So let's do a C1V1 equals C2V2. Basically, the math comes out, the moles remain constant. Right, the moles remain constant for C1V1, C2V2. A mixing question is just two dilutions in one. So I need to do a C1V1, C2V2 on the left-hand side. I also need to do a C1V1, C2V2 on the right-hand side. The most common problem I see people do is they say, oh, great, I have a C1 and a V1. This one's a C2 and V2. I'm not comparing these two together. I'm comparing the fact that the new pool that I'm swimming in is actually 30 milliliters in both cases. All right? So let's just fill our way through here. My first solution, I have a 10 milliliter solution. Multiply it by 2 molar. What's my new concentration given that my total volume is now 30? Now that my pool has now gotten bigger. For the other solution, in a similar fashion, I have 20 milliliters, 1.60 molar. What's our new concentration, again, given that we're in 30? Realistically, I really should be converting these milliliters into liters, but because we're just setting up a ratio, as long as our units are consistent, I'll make that note here, we just want to have consistent units, the same units on the left side and right side, we're still fine. And basically, we just end up with this sort of volume ratio here. I started already in 10. After you mix in an extra 20, now we're 30. You'll notice my volume ratio before and after is a third. The concentration of 2 is going to be basically multiplied by a third. So the concentration has dropped, 0.667. That's the concentration of the solution on the left side. That's the zinc chloride. On the other side here, we went 20 into 30, so we're 2/3 of 1.6. 1.6 times 2 over 3. The concentration, again, has dropped. This one now equals 1.07 molar. So both of them have been diluted by each other, although all the swimmers are more than happy swimming around this 30 ml pool together. And now as a very last step here, because these are ionic compounds, we'll see this more in chapter 3 in our course, basically water can actually come and actually dissociate your ions. I'm going to take these ions here. Let's take ZnCl2. Let's drop it in water. Water is going to separate out to become Zn plus 2 and 2Cl minus. In a similar fashion with zinc sulfate, the zinc sulfate, ZnSO4, water is going to separate the positive from the negative. This gives you here Zn plus 2 and SO4 with a negative 2 here. Water has no trouble breaking apart an ionic compound, breaking apart a positive and negative split, but you'll notice the SO4, which is a polyatomic, actually stays together. So keep the polyatomic together. Notice that this chlorine here, oh no, this chlorine is by itself. Shouldn't it be 2? In fact, charges in general are unstable. What's actually happening sort of behind the scenes here, water is actually a polar molecule. Even though water overall is neutral, because the oxygen side is a little bit more of a bully and it hogs the electrons, the oxygen side is kind of negative, the hydrogen side is kind of positive. So if in my container, I actually happen to have a zinc, like a Zn plus 2, positive charges shouldn't be stable. Well, water is actually also in solution. Water can point all its oxygen sides to try to help to stabilize the zinc. In a similar fashion with chloride, chloride shouldn't be stable by itself. We've been saying that. Cl, it's also not stable because of the negative. The water here can actually surround itself with its H sides and basically help to stabilize these charges. Water can't get rid of chlorine's charge, but it can try to spread out the charge a little bit. So all we're going to do here is a mole ratio, 0.667. For every one of these that get ripped apart, we get 1 whole zinc and 2 whole chlorines. So 1-to-1 ratio means 0.667. The chloride is going to be double this, 0.667 times 2, give or take a little bit of rounding, 1.33. Even though I'm going to lay out my work like that here, it is understood. Water would have needed to completely get rid of the zinc chloride. That's completely dissociated for me to just have the leftover ions individually. And on the other side here, we have 1.07. 1.07 molar, this is just 1-to-1. 1.07 molar, 1.07 molar. Again, it's understood that this guy here is completely gone. All right. Now, at long last, I can solve the final problem. What's the final concentrations after all this? The concentration of chloride. So we use square bracket for concentration. Sometimes they try to sneak in a 2 there, just to indicate, oh, there's a 2 there. But remember, we already dealt with the 2 with the mole ratio. In general, there should be no numbers inside the square bracket. The chloride came from my first solution. After diluting, it's 1.33. For my other solution here, we had our sulfate. Sulfate was actually a 1.07. That's fine. That came from my other solution. The zinc is a little bit problematic because the zinc actually came from the first solution. 0.667 came from the first solution. 1.07 came from the second solution here. Long story short, you just add the concentrations. This one here becomes 1.74 molar, right? Because the zinc came from both the first solution and the second solution. That should actually seem a little bit strange to you because let's imagine the zinc was actually orange juice. You take one orange juice and you mix it with another orange juice. What the math is seemingly saying here is the sweetness of one orange juice adds to the sweetness, and now the orange juice is even more sweet, right? That's sort of what we're saying here. The problem with concentration is it's intensive. It really doesn't matter how much volume, but depending on how much of these apple juices are mixed together, sometimes, most times, it just dilutes. In general, I'm just going to show you what we're doing here. You don't need to write this down all the time. Concentrations in general shouldn't add like this. It shouldn't just be the sweetness of one apple juice adds the sweetness of the other apple juice. What we're actually doing is we're actually adding the moles. I'm saying I'm in a 30 ml container. So 30 ml container. I'm going to multiply 0.667. That was my concentration. That would be the moles of the Zn plus 2 in the first solution. Our second solution, in a similar fashion, I'm still in 30. One more sig fig there. I multiply it by the 1.07 that I got from my second solution. That's the moles in your second solution. It's just that because eventually we're looking for concentration, eventually we end up dividing by 0.03 anyways, and the 0.03 just cancels out. That's why mathematically, it's like, apple juice number 1 plus apple juice number 2, suddenly we just have apple juice that's even more sweet. But nonetheless, it's just sort of the total concentration is a little bit higher. Also careful of the wording here, just especially when we deal with dilutions and mixings. Sometimes they say here, this time I mixed 10 and 20, so we're at 30, fine. I can now make the 30, I can add it up to 100. That means you're going to add up the difference until the final volume is 100. That's different from take 30 and I add an extra 100. So you can make it up to a certain volume. That's telling you the final volume, that's going to be your V2. Or in this situation, I'm saying add 10 and add 20. Each of them are independent of the volumes themselves, and you just add up the volumes one by one. All right? So that finishes off our Chem 11 review. Keep working your way through the package, and let me know if you have any questions. Thanks, guys.